Okay, good morning, everyone. And thanks to the organizers for inviting me to speak in this conference. And I'm also realizing that I'm the first speaker. So I hope I get this conference started on a good note. So I'm Roopayan. I'm currently based in IIT Bhubaneswar. I'm an assistant professor there. But the entirety of this work was done when I was a postdoc in, does this work? Yeah, okay. In University College London. So these are my collaborators. Natasha didn't send me her picture, but she's somewhere in the audience, and she'll also speak. So these four people, and I think Paul is also in the audience. The work was mainly done, but now I'm also doing some actual experiments on quantum computers with Sebastian, who is also in the audience, and Madhumita, who is going to tell you about what we're doing. So since I'm the first speaker, I can give this slide, which is quantum annealing 101. I'm sure 99.9% of the people in the audience, basically everyone knows about this, but let's just go through it once more. So the idea is you have to find the ground state of a very complicated looking potential, and you start from, let's say, somewhere here, which is some sort of a local minima. Then if you do thermal annealing, you introduce energies to this state, and then you can kind of cross over the barriers and reach your final ground state. But if you're doing it quantum mechanically, you're going to tunnel through these barriers. That's the main idea. So what annealing actually does is you start from the ground state of a very simple looking potential, and then you deform the potential slowly, so slowly that you're always in the ground state of the system. And then you end up with the global minimum, which is somewhere here. And the way you do in quantum annealing is that you use this tunneling to ensure that you're always in the ground state. That's the main idea. Now, when this happens, your ground state and excited state sometimes comes very close together for any instantaneous point in time, and then you have this gap between those two, which is delta. And we annealers know that the annealing time, which you require to do this process, would be inversely proportional to the gap at best. At worst, it is square, but at best, it is inversely proportional to the gap. And our goal, one of our goals at least, is to solve combinatorial optimization problems by mapping them to quantum Hamiltonians. And we want to do this faster than people do it classically, and that's the end goal. So, and this is the standard Hamiltonian which everybody uses. This is the Ising model. And this is used because this is an NP-complete Hamiltonian, so other NP-complete problems can be mapped into this. The idea is you start from this a state where you have a large value of this AT, which is the coefficient of this transverse field. And you start from the ground state of this kind of a Hamiltonian, and then you decrease this, and you increase the other. So this is taken from the D-wave kind of, I know I'm speaking in a different, sponsored by a different company, but this is taken from the D-wave data. But yeah, so in the end, you're left with this problem Hamiltonian. And so what you input is your H's and J's, which defines the problem, and you get output the spin states that gives you the solutions. Crucially, note that the transverse field is the only field that can tunnel between two computational states, and this is going to play a crucial role in what I'm going to say. So this is also the initial state, and also the only tunneling element in your system. Great. So if you are sleepy in the morning, I hope, or jet lagged, this is the TLDR of my talk. The first thing is I'm going to talk about the issue of quantum annealing, which is that adiabaticity is severely affected by exponential gap closures during the anneal. And I'm going to look at solutions. The solution which I'm going to propose is utilization of catalyst, which sometimes helps avoid the transition points. But what I'm going to try to do is put some method behind finding a good catalyst. And that's the goal, basically, of the talk. And the conclusion is that I'll show you that n-local catalysts are going to be necessary. You have to increase the locality of your flip terms, basically. And n-local, I mean this 2 local means you flip 2 spins at a time, 3 local means 3, and 4 local means 4, and so on. But you're also going to see that some of them are better than the others in the problems which I'm going to show. So with that, let me begin my talk. So this is the structure. I will start with talking about the bottleneck first. Just recap of quantum phase transitions. Sure, it's not the only bottleneck, but this is the most important bottleneck. Then I'll talk about the maximum weighted independent set problem, which is what I'm going to focus on. And then I'm going to use some toy models to figure out some good catalysts, and then try to figure out a general n-local catalyst. And I'm going to briefly tell you how everything connects to the idea to spin models, which people have studied a lot in classically before. And then I'm going to conclude. So let's begin. So for quantum phase transitions, so if you have a finite size system, your energy gap always is some function of that size, okay? And typically, there are exceptions, typically if you have first order phase transitions, then this gap scales exponentially with system size. Like it's very small if you increase L. And in an order parameter, this is the one how you define first order phase transitions, there is a discontinuous jump. So this is typical, but this is a general definition of first order phase transition. On the other hand, in second order phase transitions, you have this, typically again, you have the gap scaling polynomially with system size. And this is much more benign. And when you prepare any state, let's say in Rydberg atom systems, for example, they usually utilize the fact that the phase transition, they need to go through the second order, which is why they can prepare the states. And also it's characterized by continuous variation of order parameter. Now, these first order phase transitions are the worst enemies of adiabatic quantum computation because clearly you're going to require an exponentially long time to prepare the state. So if you're trying to make something which is NP hard classically, and you're getting back something which is exponentially long to prepare, you're getting no advantage at all. So that's the problem. So people have tried to make it better, and mostly the results is you can make this A as small as possible. There are very rare results, for example, this paper by Nishimori, where they showed that in p-spin models, they've introduced something like a non-stochastic, I'll come to that later, XXXX, like 5 local interactions, you can make the first order transitions to second order. But this is the problem. So let's now look at the physics behind the problem. So what I told you is first order phase transitions are typical culprits of gap scaling exponentially. But you need to know that there are 2 kinds of such things which can happen. The first kind is a first order phase transition. Okay. Oh, my laptop died. Just a moment. No, it's fine. Somehow, sometimes it just restarts on its own. No, it's fine. It'll barely take a couple of minutes. 1 minute. Yeah, so what I was going to tell you about is there are 2 kinds of first order phase transitions that usually happens during a quantum anneal. So let's see, PowerPoint. Just a moment. So clearly I am going to be affected by the 10 a.m. thing. Oh, come on. Just a moment. Yeah, I was here. So there were 2 kinds of first order phase transition. One is when you have a ferropara transition. Typically in the transverse Ising model, which is 1D, the ferropara transition is second order. But then when you look at something like a p-spin model, this ferropara transition becomes first order, and that happens because now at the transition point, you have just 2 states which are involved in a transition. Everything else lies at an energy which is much higher than these 2 states, and that's how it becomes first order transition. So for example, what I'm showing here is on one side you have the ferromagnetic state as an excited state, where on the other side you have it on the ground state. And then you go through a first order transition. I will tell you why. The other scenario is, which I'm going to focus on mostly, is perturbative crossings, where you are in a regime where your driver acts perturbatively to your problem Hamiltonian. And then when that happens, since your problem Hamiltonian is just the Ising model, the eigenstates of that are just computational states. And then this means that your ground and excited states will have maximal overlap with just a single computational state. And if this ground and excited then kind of switches across a particular point during your anneal, then you can get a first order phase transition. And this specifically happens when you have a large Hamming distance. And you're going to see why. So if you look at this kind of a 2x2 Hamiltonian, effective Hamiltonian of the ground and excited state, so let's look at the first scenario where you have a paramagnetic state on one side. So this is the paramagnetic ground state, while this is the ferromagnetic state. So the I denotes the computational state. So if you compute this off-diagonal element, and remember, this off-diagonal element is what actually gives you the gap. You can just diagonalize it and find out. Then you can see that this basically, the overlap is proportional to L by square root of 2 to the L. Because as you saw before, it was like a summation of sigma x's, so it flips only one spin at a time. So it can only connect this state to L number of states to the paramagnetic state, which automatically means because of this prefactor, you can only have something which is proportional to 1 by square root of 2 to the L, and which means it is exponentially small in system size, which means the gap becomes exponentially small, and this is exactly what happens in p-spin model. In Grover, it's even worse. You don't even have this L here. So this is one kind. The other kind is when you have a large, this perturbative transition, when you have a large Hamming distance between these two computational states, then actually this term is exactly 0. There is no connection at all because you're flipping only one spin at a time due to sigma x. Then to find out what actually is the gap, you need to do a perturbative calculation, and it so turns out that you can only do it at like Lth order. Let's say your Hamming distance is L, then you can only connect at Lth order of perturbation, which means each time you apply your sigma x, you're going to go to a state which is lying somewhere here, which means you're going to get a delta E2 approximately each time in the denominator. And therefore, again, you get something which is exponential in system size. So these are the two kinds, and I'm going to focus on the next one, the second one. And the crucial thing which you should know is that this basically means that transition to excited states are unavoidable via sigma x drivers, because otherwise you need to go really, really slowly, which is not possible. So if you just do sigma x drivers, you're going to transition to excited states. You cannot help it. The gaps are so small in these scenarios. Great. So how can we mitigate this? So we can learn from classical a bit. So classical people also have found similar things like critical slowing down. So phase transitions typically mean existence of some kind of order in the phases. So there is order parameters, symmetry breaking, and so on and so forth. Classical phase transitions are known to show long-range correlations and order. For example, Ising transition. You have similar things in quantum phase transitions as well. And also, when you do this classical Monte Carlo single-site simulations, people found that they exhibit something called a critical slowing down, where when you're doing this Monte Carlo, when you're reaching close to the critical point, you actually only converge very slowly to your ground state. Okay? So the solution which people found there was cluster algorithms. Like these are the two most famous cluster algorithms, Swensden, Wang, and Wolf. So they were flipping large connected clusters to kind of mimicking the correlations in your system. Now the question is, does doing the same for quantum systems help? And this is where the catalysts come into being, where you are increasing the number of spin flips. So with that, let me go into the problem which I'm going to look at. This is an NP-complete problem. And this is one of the simple examples of this problem. So think about a graph with vertices and edges. And each of the graph nodes has some weights on it. The job is to find out the set of nodes which are vertices. I'll use nodes and vertices interchangeably. Vertices which are not connected to each other, but which have the maximum total weight. So that is by maximum weighted independent set. Okay? So in this graph, this maximum weighted independent set is a set of these 3 points. Because if you add them together, you have 9. These 6 are also independent, by the way, but they add up to 6. So that is not the maximum independent set. So this is actually an NP-complete problem to find this in a general graph. So we are going to use this to kind of do our annealing and study how to reduce these perturbative transitions. So how do we write this problem mathematically? Well, to write this problem mathematically, as we learned yesterday, you write a cost function. You write a cost function which penalizes taking 2 points which are connected, which is this penalizing term. So you have an interaction. And then the term which puts the weights. So you have to find the configuration which maximizes this HP. It so turns out for this maximum independent set, you have to choose each of these j's to be greater than the minimum of the weights so that you always maintain the independence condition. If you don't do that, you're going to lose the independence condition. You're going to get sub-solutions which are not independent. That's the most important thing. And then you map it to the Ising model, because that's what we can do with a quantum annealer. And since it's a 0 and 1, it's a qubit, so you can map it to sigma z's. Look at how the jij's have come also on the local qubits. So this is a feature which comes. This is not wrong. This actually happens. And the solution is the upspin set. For example, in this graph, the solution is the set of points which I have marked in red. And I just want to point out one other thing. Typically, in such scenarios, even the lowest lying excited states are independent sets. So what I'm showing here on the left is the first excited state, where the green points are the kind of the upspins. So, and this is going to play a part when I develop the toy models, that the first excited states are also going to be independent, just not maximally weighted. So now that we know how to map everything to the Ising model, let's look at some toy problems, because that's what we do as physicists. We develop toy problems and try to figure out what's going on there, and then apply it to unknown problems. Great. So the toy problem which we are going to look at is the bi-click model, where you have connections in between two partitions, but nothing inside. So this is the standard annealing protocol which I'm going to use. It's going to be a linear protocol. There's nothing funny going on here. And as I said, the driver is this sigma x driver. So here I have weighted this partition on the right to be the, okay, this works. Yeah, the partition on the right to be the greater weight. So then this becomes the independent set. That's why I've plotted it with upspins. And this is the other one. So the solution is some kind of order, right? But when can we develop phase transitions in this system? That's the question, because this is a toy model. Well, to do that, you need to check out what happens when you flip some spins. You calculate the energy cost of flipping spins. That's how you develop the understanding behind this. So if you flip the left spin, you get some energy cost. This J is basically the interaction between them. If you flip the right spin, you get some other energy cost. Now, it's weird that you don't see a J happening when you still have this kind of a term which is not satisfied, is because of the local, as I showed you, the local term also has a J in it. And then you do two flip flips and so on and so forth, and then you reach a situation where you do all spin flips. So when you do all spin flips, then you can find out that the energy difference, energy cost of doing all spin flips is just 4 into the difference between these two weights. So now you can develop a competition. There is a situation if this difference is less than, let's say, this particular situation, where it was just W5, then this becomes the first excited state. So the lowest energy cost will be flipping all the spins and not just flipping one spin. And this is essential to create like a situation where you can have a phase transition, because then your lowest excitation cannot be accessed at low orders of perturbation theory, which means that it has a very loud, the sigma x cannot access it. So if a situation arises that during your anneal, your ground and first excited state is switching, that will go through a phase transition. So that's the goal of this toy model. Of course, this is a necessary condition. It's not sufficient. A sufficient condition also involves choosing that these sector has less spins and so on and so forth, but let's not go into that. But yes, this is why we are choosing this bi-click system, because we have complete control over when phase transitions happen. And you can generalize it, which will be there later. Anyway, so now we are going to add a catalyst and see what happens, okay, and see how it improves this, this annealing. So how to choose a catalyst? That's the question. So as a theorist, your first idea would be, if I could connect the almost two degenerate states involved in the transition directly, then I can open up a gap, right? That's the idea, because that gives you the matrix element. And you saw that there was long-range order present in the solutions, which means that local catalysts cannot work for a general scenario. You have to have some non-locality in the catalyst, and you have to have like a lot of spin flips at the same time. So this non-local catalyst, it can cause level repulsion to open up a gap. So previously, if you remember the 2x2 matrix, I told you this off-diagonal was 0. But what I'm telling you is now if you add a direct coupling between them, then you're going to get an off-diagonal element here, which is proportional to the strength of the catalyst, and that is going to give you the gap. So that is a theorist solution, that this will, if you know the states, you connect them, you get a gap, direct tunneling. Great. And I'm going to show you that it works, just to be sure. So for that, I'm going to consider 3 situations. One is the vanilla annealing, where you just have the X driver. Then you have something called an XX catalyst, where you add an XX interaction on each of the bonds which you have the ZZ interaction. That's why you have 2 colors here. And another scenario where we add the perfect catalyst, which is connecting all the spins and flipping them all together at the same time. We call this the product catalyst because it is the product of sigma x's. Great. Now some plots. Everything is as expected, but it's good to see them in actual plots. So for example, if you do the annealing, then if you have no catalyst, you get at a certain value of S is the anneal parameter, you get a very low gap. But now if you introduce this product catalyst, you completely vanish, the gap completely vanishes, and you have to trust me that there is no gap closing here. I've just plotted the region of gap closing. This excess catalyst is not too bad either. It improves, but it doesn't completely remove it, and that's going to play a part in future, the fact that it's partially at least removes it. Now if you go to the order parameter, because first order phase transition order parameter and so on, then you're going to see the order parameter here is a difference in magnetization between these 2 clicks, which is some kind of a staggered magnetization. And you see that if you have no catalyst, then it's like a very sharp transition. If you have XX, it gets smoothened out a bit. But if you have this product catalyst, it's completely smooth. Fine. But what about finite size scaling? The other good thing about toy models is you can do scaling, because you can just scale up these 2 clicks and you can get the data for the minimum energy gap during the anneal. And clearly it's exponential for both no catalyst and XX catalyst, but XX catalyst does change the slope, so it's helping still. This A factor, which I told you in the beginning in front, exponential AL, this A is getting changed. Whereas if you have the product catalyst, nothing happens. It's just completely flat. Good. That's very good. But it's useless. It's useless because that is a very, very specific toy model. It allows us to predict the catalyst, but in general models, you don't have this structure. So the best you can do is kind of learn from this model and utilize what you know to other general models. So we have to rely on imperfect catalysts, but with non-locality. That's the first thing you should understand, that we learned that we need to use n-local catalysts. But the question is, how do we select which size to put it on in a random graph? Well, the way to do that is go to the toy models again, and now you look at some n-local catalysts. You try to do as much of different simulations as you can to understand what's going on. So here, what I'm showing you is, again, this toy model with size 5, which means 3 and 2. So now I have XX couplings. It's not just the HCXX, which I'm showing there. It's XX couplings, where I'm adding 0, 1, 2, up to 10 couplings on various places in the system. So this denotes the number of couplings I've added to the system, and each, let's say you have 2 couplings, you can add it in various positions. So each point denotes a configuration of such positions. And the color of the points denotes the number of, like, the density of points in that region. So red denotes a high density of points, and blue denotes a low density of points. So this is for 5, this is for XXX, 3 local, 4 local, and then again for 7, this is XX. We couldn't go beyond that because there is around 2 million points, which is here. So beyond that, it's almost impossible to scale up. So the general trend is that clearly increased n-locality and more couplings help. So more couplings help until you reach a saturation, and we can explain that. I'm not going to go into that much of details. You can explain why it only helps up to a certain point. But there's something very interesting. There are some optimal configurations which do exist, even for low n-locality, and which kind of, there's a lot of them for L equal to 7. So ideally, we would like to do a system size scaling for all 2 million of the configurations, but we can't. So we choose some specific configurations and try to see how the energy gap, minimum energy gap, varies with system size. And for that, we choose to compare with, of course, a no catalyst situation with something where we connect all the couplings between all the vertices, and then you connect the CXX, which is when you have a ZZ coupling, you connect additional XX. The complement of that, that is, you connect an XX coupling where you don't have any ZZ couplings, and some optimal configuration of catalysts from the previous graph. So one thing is that this optimal catalyst configuration is somehow completely completely size independent. It works, this black line, it works for all system sizes. On the other hand, the other ones kind of scale down, and they're more or less pretty similar to each other. So we are going to say that, okay, maybe HCXX or HCXXX was not so bad. But clearly, increasing the n-locality is helping. Great, we learned things which work. We can also learn things which doesn't work. There are some redundant couplings in this MWIS problem. And this is very interesting. And this is kind of peculiar to this maximum weighted independent set problem itself. And to see that, you need to generalize what we did before into a tripartite system. So for a tripartite system, something funny happens. You cannot satisfy all 3 bonds, because these are antiferromagnetic. If I haven't mentioned before, these are all positive J's. So you cannot have all 3 antiferromagnetic to each other. So there will be one unsatisfied bond, which means the solution would have only one upspin. The maximum independent set would have only one block. Okay. So now, this means if you flip all the spins together, which the product catalyst does, it will take you to a set which is not independent. Then you will not satisfy kind of, you have 2 upspins. So that is not in your independent set at all, which means that will have a much higher energy compared to the ground state of your problem. Okay. And because if you have a much higher energy than the ground state of your problem, which means it's not going to be your first or second or third excited state at all, which means if you connect it via a catalyst, it's not going to help you. It's not the first excited state. So what's the point in connecting it via a catalyst? There's not much point either. And that's exactly what you see in this plot, which is like a scaled up version of what you see in the left. So the idea is here you see this product catalyst and the no catalyst, there's the blue and the black, are kind of overlapping with each other, showing the product catalyst doesn't do anything at all, while the red one, which is XX, helps. And there is an optimal catalyst here. The optimal catalyst is basically flipping 2 blocks of spins at a time, and that perfectly removes the transition. So you cannot flip 3 blocks of spins at a time here. You can only flip 2 blocks of spins. That's something we learned from this. So these kind of loops I will call frustrated loops for obvious reasons, because there's some frustration involved. Great. So this means I can define a hierarchy of couplings which is required to be added. So if I look at all the subgraphs of a big maybe graph where I should add the couplings, all of them will look something like this. So there is like 2 local, 3 local, 4 local. But what I'm saying is for the 3 local couplings, you shouldn't add them when your subgraph looks like a triangle. For the 4 local coupling, you can add it for square and this tree diagram, but you cannot add it when your subgraph looks like a square with a diagonal involved. That's the idea. So these are redundant couplings, and these kind of polynomially reduces the number of couplings you should add. So there is this hierarchy which you see here. If you're confused by this, I have an example in a graph. So what I'm saying is, let's say your graph looks something like this. What I'm telling you is this red subgraph, you shouldn't add XXX catalyst if you want to. If you have a 4 local catalyst, you shouldn't add it to this orange graph. You should add it to this green graph, the XXX catalyst, or to this light green graph. That's the main idea. And keeping the same graph, if I put in some values and kind of induce a transition, this happens like in the reverse order. I didn't put the values like this. I just had the values and then got the transition. I can show you that the transition actually gets mitigated when you add this 3 local catalysts. So initially when you have no catalyst, you have a low energy gap, but then if you add excess catalyst, it improves a bit. But if you add the 3 local catalyst, it improves much further, and you basically don't have the transition at all, almost. So this is like a single example. However, we did a lot of statistics. Luca was the driving force behind this work, where we did it for random graphs. So we chose 2 families of graphs, the Erdős-Renyi graph and the Barabasi-Albert graph. So for those of you who don't know what these graphs are, well, to put it simply, these graphs differ in the degree distribution. Degree meaning the number of vertices a particular vertex is connected to by the edges. So the degree distribution of the Erdős-Renyi graph looks like a Gaussian, while the degree distribution of the Barabasi-Albert graph looks like a power law, meaning there are many vertices which have no connectivity at all, while there are very few vertices which have high connectivity. So these are like hubs and no hubs, and this is related to some social, the World Wide Web structure in the world and so on and so forth, but let's not go into that. So we thought we are going to see some difference in the kind of catalysts we need, but we didn't because we could only do small system sizes. I'm coming to that later. So we did a lot of statistics. These are 10,000 points here of 10,000 different graphs. And the main idea is this red line which you're seeing here is the point where you get no return. So where your energy gap with the catalyst is exactly equal to the energy gap without the catalyst. So anything above this line, any point above this line shows that your catalyst is improving the energy gap. And you see practically most of the points is above this line. So statistically there is a significant improvement, and this inset here is plotting it in some sort of a ball and socket diagram where you have this 3 sigma bars and so on and so forth. It's not that important. The main thing that's important is you're getting improvement with XX catalyst. So this is just XX couplings. You can do the same thing for the Barabasi-Albert graph, and you see a very similar structure on the right. Again, most of the points lie above that line of equality. So it means that catalyst is helping to improve the energy gap. And we did a small finite size scaling where we are comparing now the geometric mean because we are actually calculating ratios. And we see that for different kinds of graphs, if you do lots of these are like 10,000 different points for each point. So there's a lot of averaging going on. I'm not going to claim it improves with system size. I'm just going to say that it doesn't change with system size because it's for coiled systems. But the good thing is clearly XX catalyst works statistically, and that's what we are concerned about. Great. We go further. We go now XXX catalyst, which is the N locality improvement. Again, I do a lot of simulations, and again, this line denotes the line of no return. Anything above this line means it's good. And if you look at the first 2 plots, the first plot is with XX. The second plot is with XXX. So what I'm showing here is that if you, visually also, you can see the points getting lifted upwards. And if you're not convinced, you look at that rightmost plot where I'm showing XXX on the y-axis and XX on the x-axis, and clearly all the points are above that line, so means XXX further improves most of the situations than XX, which is good. And I have no time to talk about these marked points, this red and blue. So red point is a situation where you get a phase transition when you add a catalyst, but the green is when you get improved. But we have been able to show that statistically, chances of getting a red point is much less than the green point. So that is, like, we can show that analytically why that happens. So the lesson is your n-local catalysts somehow sometimes manage to hybridize ground states with low-lying excited states to open up a gap. Now, the effectiveness depends on the presence of structure in the problem. So, for example, Grover, there is no structure. There is no low-lying excited state. You can't do anything with n-local catalyst. But with problems with structures, you can do something with it. That's the entire idea. And the proposal is, in your problem, you do a hierarchical addition of n-local catalysts till improvement is seen, or till your system limits are reached, or whatever it is, like till no improvement, it should be till no improvement is seen. So you add it, and at some point of time you see that, okay, there is no more improvement, you decide to stop, that's going. So this is the main idea of the thing. So how much time do I have left?
2 more minutes.
2 more minutes, okay.
2 more minutes until 5 minutes.
Okay. Okay, 7 minutes, oh, that's good, I'm doing good. So I just have a short demonstration of what happens if you discretize this. I understand that this is a continuous time, probably talk, but still, we did some discrete things. So, and it's what you expect. You discretize a continuous thing, you get the same improvements. There's no huge deal going on here. It's just that I wanted to show that this n-local couplings can easily be represented as gates which have ladders of C-naughts. And these ladders of C-naughts are actually linear in the n locality. So it's like a linear cost to prepare these gates. And of course, what you do is you kind of calculate the fidelity with the actual ground state, and you can show that this P denotes the trotter depth, basically. So you can show that if you add a catalyst, you can get a much higher fidelity with the same trotter depth. But then in each trotter step, you actually have more number of gates if you add a catalyst, because you have to remember you're using ladders of C0. So the actual correct thing to look at would be the total number of gates. And even then, this shows a lot of improvement, that if you have the same number of gates, if you use the gates to make a catalyst instead of don't make a catalyst, then for the same number of gates, you get a much higher fidelity with the exact ground state than when you don't have it. So this can be summarized by saying that there's an order of magnitude reduction in the number of gates which you require to prepare a ground state if you use a catalyst. Good. A short digression. For some of you who have already been in quantum annealing for quite a while, you know that there's an idea of non-stochasticity. So what I didn't mention in all of my previous results was I was also always using the catalyst with a minus sign in front. That is something called a stochastic catalyst. Non-stochastic catalyst has a positive sign in front. So it has been said that it improves annealing in some places, but for our scenario, it doesn't. And you can see the simulations for the toy models where you're going to see this non-stochastic catalyst, which is, so I already had a minus sign there, so minus of that gives you plus. So then this dashed line becomes non-stochastic. It makes things worse for the same catalyst, so it does not improve. And there is a reason for that, and the reason is we're dealing with perturbative crossings. So imagine your V is your catalyst. That's what I'm writing the V. And your psi n 0 is the states which is just prepared from the problem and the driver. So the n equal to 0 then gives you the ground state of the problem. So what this is computing is the correction due to the catalyst to, let's say, any energy state. And let's consider n equal to 0, then correction to the ground state of the problem. And I've written it till the third order of perturbation. Crucial thing is, since this is a perturbative crossing, your eigenstates are perturbation across computational states. So this means that you can replace this, all the psi n zeros and everything here by the corresponding computational states. This in turn means each of these matrix elements are either fully positive or fully negative depending on you're using non-stochastic or stochastic catalysts. Okay. Now if you look at the perturbation theory, then you can see that the second order term is always negative for the ground state because m is the excited state, so denominator is always negative. The third order term, the numerator for stochastic catalysts is negative. The denominator is positive. So it gives you a negative correction. So it pulls down the ground state if you have stochastic catalyst. On the other hand, if you have a non-stochastic catalyst, the third order term will give you a positive contribution. So second order and third order term are against each other. So it may or may not give you an improvement if you use a non-stochastic catalyst. And this is only true for perturbative crossings because you can write it in terms of this computational states, basically. On the other hand, I showed you that Nishimori showed already that for p-spin model, you have improvement for non-stochastic catalysts. And I'm just going to briefly explain why is that. I already told you that that transition for the p-spin model, which is the ferro to para transition, is different from our transition. And this is the p-spin model. Basically, it's an n local term already in the p local term, rather, in the sigma z's. And then this is the annealing. And this is the catalyst we use, this n local catalyst to the power k, makes that n locality. And this has an angular momentum conservation, so you can go to decay states and you can do large system sizes here. And you can see that in all these plots, the no catalyst and the stochastic catalyst makes things even worse than no catalyst, while the non-stochastic catalyst increases the energy gap. And if you look at the scaling, the same thing happens. This green is non-stochastic. The energy gap is quite more than the other two. And to understand why that happens, you need to look at what happens around the transition. So it so turns out that if you look at the transition, when you have no catalyst and a stochastic catalyst, the ground and first excited states are quite different from each other. So this is plotted in the decay state basis. So the decay state basis, the paramagnetic state is a Gaussian in the middle of the decay state, and the ferromagnetic state is like the last state in the decay state, because this is like the angular momentum. So this is the standard thing which happens in first order transition. You have a coexistence, and then you have a switching. But now when you introduce, if your catalyst sign is negative, then what happens is it reduces the energy for all the paramagnetic states in the same direction. So there is no improvement at all. But now if you use a positive catalyst, like which is a non-stochastic catalyst, it induces a competition in energies in the paramagnetic sector itself. So near the phase transition, the first excited state is no longer the ferromagnetic state. It happens much earlier. It's another semi-paramagnetic state if you like it. And the semi-paramagnetic state has a large overlap with your ground state itself. Now, if you have an overlap, which means you have a matrix element already. Already having a matrix element means you have a gap. So that's how it improves the gap by energetic competition introduced by non-stochastic catalysts early on. It changes the excited state itself. And that's how you're changing the gap. Here, in our scenario, I was introducing tunneling between the two states. But in the p-spin scenario, the n-local catalyst changes the excited state itself, and that somehow has an overlap with the ground state, and that induces a gap. So this is quite different from what we have, and that is why non-stochasticity works here. And in the last minute, I will tell you one of my recent works with Sogato, which involves what's bad for quantum annealing is good for quantum sensing. Because we showed that first order phase transitions, if you use the order parameter as an observable, you can do very good quantum sensing. And for quantum sensing, the parameter which we need to look at is the quantum Fisher information. And it so turns out that is equal to the 4 times the fidelity susceptibility. And for the more knowledgeable people, the fidelity susceptibility is inversely proportional to the energy gap squared of the problem. So since in the first order phase transition we had an exponentially small energy gap, it means that the Fisher information will now scale exponentially with system size. And you can now prepare very good sensors with very few qubits. That's the idea. And this got published a few months back. But so it's not all bad. I've been saying that small energy gap is bad and so on and so forth, but it's actually good for some other purpose. So that brings me to the end of my talk, and I think I'm more or less on time. So what I wanted to say is to mitigate perturbative crossings, increasing quantum tunneling for n-local catalyst is probably the most viable path, because clearly the physics tells me that I need to increase tunneling if I want to go from one state to another. The next stage where we want to do is kind of introduce variation, combine this with schedule optimizations like variational algorithms like QAOA and quantum random walks and so on, add these terms and see whether they show further improvement. So these couplings which we are using are not native in the current annealers, but specific encodings can help. I think Paul will talk about that later. We have some ideas of how we can do this. And what I want to I'm working on a bit is the entanglement bottleneck in quantum annealing. What is it all about? Because there's been very few papers which have comprehensively shown in a model-independent way what is exactly the bottleneck in entanglement. And currently I'm working with Sebastian on understanding some structure of large random graphs using reverse annealing in D-wave, and also with Madhumita and Sebastian to prepare critical states for sensing. So that's where we are at. We are now trying to implement these ideas in actual quantum devices. And thank you for your attention, and I'll be happy to take any questions.
Okay, maybe the next speaker can already set up the things. Yeah, but are there questions from the audience? Over there, yes.
Well, thanks for the talk. I have a question. Have you tried including counter-adiabatic driving methods in your test and then check how they compare with your n-local catalyst proposal?
No, but I think in the extreme cases, this n-local catalyst is probably going to give you this, what do you call it? You have this diabatic kind of path, which will the ideal n-local catalyst would be the ideal diabatic path, possibly. That's to remove the transition. That's quite possible. Like you have this shortcuts to adiabaticity, right? That's people study. Maybe the path, the optimal path to shortcut to adiabaticity will match with the optimal catalyst. It can happen.
Okay, thanks. And very short one. Beyond a digitalization of your annealing protocol, do you have in mind any analog platforms where you can actually implement these catalysts?
The catalyst, digital ones, I know. You asking for analog? Analog. The analog ones are much harder, I would say, because I don't know yet any analog platform which can give XX flipping. So that is why we moved to digital, because that's where we know we can actually probably see something improving.
I'll be talking about that in my talk.
Yes. Paul will be saying something. Like there's some situations where it works, but yeah.
All right, any further questions from the audience? Yes.
Thanks for the very nice talk. The results that you showed are for the MWIS problem. Have you also tried this for other problems?
So the first thing is the MWIS problem is mappable to other problems, right? So it's only going to have a polynomial overhead. The other thing is when we simulated those graphs, for example, we kind of did a spin glass kind of took like random things, except we just kept this constraint that the interaction is greater than the local fields. That's the only constraint we kept. But other than that, it was completely spin glass type problem. So these should be mappable to spin glass, but we don't know what happens when you remove that constraint. That's something we need to check, yes.
All right. Any further questions? Doesn't seem so. I did actually have one.
Oh, sure.
Maybe you already mentioned that whether the catalyst works or not has to do with the structure of the problem, right? Did you consider maybe, or if you have unstructured problems, you get no better than Grover speedup, but sometimes Grover is already better than nothing, right?
Yeah.
Did you consider maybe using like some sort of randomized catalyst to destroy structure and get at least the Grover?
So we haven't done that, but there is I think Natasha is using some kind of like an ordered way of improving catalyst after each iteration in a manner, improving where you put the catalyst. One of the ideas which we had initially, which we could not do it, is trying to use machine learning to figure out like some kind of optimal random catalyst or something. But yeah, the best random catalyst we did was that for toy models, where we simulated everything and saw what's happening there. So.
All right, then thanks again, Roopayan, for your talk.